us throughout the entire design and construction process and outfitting. So everything you see in this lab was carefully reviewed to make sure it wouldn't contaminate the sample so we can get the most scientific benefit out of this return.
So can you tell us a little bit about how long it will take to fully reveal the sample and where the sample will live?
Yeah, so the sample's permanent home is this lab behind us. But what will actually happen next is we'll continue taking the tag SAM apart. So right now we have this incredible view of the sample into the tag SAM. We're looking into the part that touched the asteroid Bennu. We're actually going to take those parts off to get a little further in so that we can then distribute that sample into bulk sample handling trays, which are triangular and look sort of like deep dish pizzas.
And for scientists interested, how will they eventually be able to request a sample?
So in about 6 months, we will release a sample catalog, which will give scientists from all around, even beyond the sample analysis team, enough information to start to think about what science questions they want to ask, and they can propose studies and specific quantities of sample they would like to use. And then those requests will be reviewed by a peer review allocation board. And then those who are granted their requests will get samples in the next 9 months or so.
All right, well, Nicole, thank you so much for joining us today. And as you can see, we are just beginning this process here at Johnson Space Center, but there is much more work to do. So we'll send it back to the auditorium for now.
After its 7-year journey, it's amazing to finally see a glimpse of the samples that were captured from asteroid Bennu. Not only will this mission help us dive deeper into how planets formed and how life began, it also will allow for current and future scientists to make discoveries for years to come. Now, to help us take a closer look into what we've learned so far, we have a panel of individuals who played key roles in the OSIRIS-REx mission. Please welcome back NASA Administrator Bill Nelson, OSIRIS-REx Principal Investigator Professor Dante Loretta, OSIRIS-REx Astro Materials Curator Dr. Francis McCubbin, Goddard Space Flight Center Sample Analyst Dr. Daniel Glavin, and Director of the Planetary Science Division Dr. Lori Glaze. I know you all have a lot to say, so let's get started. Administrator Nelson, let's start with you.
Well, this is an example of why we do make the impossible possible. It's a team that no matter where we are, we all work together. You all know Pam Melroy and Bob Cabana, and we, the three of us, operate as a crew. It's because of that unity, that relationship, that watching each other's back, that we get so much done. And here is another example of what you've seen today. Now, I want you all to hear from the real experts. So take it away, panel.
Thank you, Administrator Nelson. Next up, we have Dr. Francis McCubbin, Astro Materials Curator.
Thanks, everyone. So we are thrilled to have the OSIRIS-REx sample collection here at NASA's Johnson Space Center. And we look forward to the exciting discoveries that are going to be made by the science team with those samples. Over the next 6 months, the curation team and the science team are going to be working closely together to develop a sample catalog that, once released, will provide an opportunity for scientists around the world to request material to study Bennu in their own labs. For now, the curation team is hard at work, carefully and meticulously disassembling the hardware, containerizing asteroid material, and documenting everything they do every step of the way. All of this work takes place inside of a glove box. And those glove boxes are necessary to keep these samples as pristine as the day that the sample landed in Utah. Now, as you've heard, we have a bounty of sample on our hands already, and we're not even inside of tag SAM. The views here are amazing of this sample, and they're only going to get better. Now, as you can imagine, working with hands inside of a glove box, Within a clean lab is hard, challenging work, and it does not go quickly. But we need to do this right. And in fact, we have a lot of heritage of this working really well to keep samples pristine over multi-decadal timescales. If we just look at our Apollo collection, the samples that were returned in the late 60s and early 70s when humans first went to the moon, to this day, we still get hundreds of sample requests and allocate hundreds of samples to answer questions that we didn't even think to ask at the time that those samples were returned. This is the true value of sample return and of curation and keeping these samples pristine. It allows us to answer questions that would not be possible with the technology of the time. In fact, like all of our astromaterials collections, the OSIRIS-REx collection is going to be conserved so that scientists that aren't even born yet are going to have the opportunity to answer questions about our universe with these samples using technology that has not even been invented. This is the legacy of OSIRIS-REx and of sample return broadly. And now let's hear some of those science results from the science team.
Thank you, Francis. Next up. Great job, Francis. Next up, we have Professor Dante Loretta, the principal investigator for the OSIRIS-REx program.
All right, thank you, Shaniqua, and thank you, Administrator Nelson, and to Dr. McCubbin. I just want to start out by saying what an honor it is to be on stage here talking about the amazing results. And I want to talk to the young people in the audience because NASA for me when I was a kid was always like a guiding light, like a dream. To work for NASA meant to be part of the best, to be at the forefront of human exploration. And to see this dream coming true today is beyond words for me. So let's start out with taking a look at what we've gotten into so far. As Francis said, it's been going slow and meticulous, but the science is already starting. So if we could bring up my first graphic. So what you're seeing here on the left side is the first look at the tag SAM. So you've got the science canister, that's like the vault that protected the sample on the return journey home. And sitting inside there is the tag SAM. That's the device that actually touched the surface of Bennu, collected sample, kind of like a vacuum cleaner, except in reverse, because we were in space with no air. We brought our own air, and pushed that material inside. It's basically like an air filter. First thing we noticed was that there was black dust and particles all around the outer edge where the seal had laid down and protected that precious material. And the reason it got pushed out was because we had under that nitrogen purge to keep it, the Earth's atmosphere away from it, and it pushed all the dust and particles to the edge of the canister. And I drew a little white rectangle there on the deck, and that's zoomed in on the image on the right there. And already this is scientific treasure. We see dust particles and we see millimeter particles, which are like a 1/16 of an inch or so in size. And we swept some of that material and we got it to the sample analysis, what I called my Tiger team. They were here at Johnson Space Center. The electron microscopes were fired up and ready. All the other instruments were ready to go. And we got those particles in on the third day that we had the sample here in Houston on September 27th. So let's take a look at some of the first results that we got from those particles. And boy, did we really nail it. So here I'm just showing you 4 different examples. This is taken with an electron microscope. Electrons kind of behave like light waves, but they have much shorter wavelengths, so you can see very, very fine details that you would never be able to see with an optical microscope. The first panel there in the upper left, those are the water-bearing clay minerals, and they have this fibrous kind of structure. We call this serpentine because they look like serpents or snakes inside the sample. And they have water locked inside their crystal structure. And I want to stop and think about what that means. That water, that is how we think water got to the Earth. The reason that Earth is a habitable world, that we have oceans and lakes and rivers and rain, is because these clay minerals like the ones we're seeing from Bennu, landed on Earth 4 billion years ago to 4.5 billion years ago, making our world habitable. So we're seeing the way that water got incorporated into solid material and then ultimately into planets, and not just Earth, but probably Venus and Mars also had abundant water as well. The next one on the upper right, you can see the hexagon. It's got that really like stop sign kind of shape, and that's characteristic of a sulfide mineral. If we could go back, yes, thank you. And sulfur is also a critical element for planetary evolution. It determines how quickly things melt, and it's also critical for biology. A lot of the amino acids that give structure to our proteins use sulfur to link and provide those bridges. And then the bottom two there are iron oxide minerals called magnetite, or you might know them as a lodestone. They react to the magnetic fields. The one on the lower left is framboidal, like a raspberry, and the one on the right are plate-like. And especially those platey ones might be really important for organic evolution. They might catalyze certain reactions. So we're looking at the kinds of minerals that may have played essential roles in the origin of life on Earth. Now we can go to the next graphic. One of the coolest techniques that we have here at Johnson Space Center is X-ray computed tomography. It's like a CAT scan. So without cutting into the rock, we can actually look inside. We can see the textures and the distributions of the minerals. This helps us intelligently select areas where we want to make cuts so that we get the most exciting science results. It also gives us a good sense of the size and shape of the particle. This is the biggest one. It's about 2 millimeters across. And you can see here in red those sulfide minerals. I'm particularly fond of those. I'm an expert in sulfide mineralogy, and I can't wait to get inside and look in great detail at what's going on here. And now let's go to the last graphic. We saw Administrator Nelson show you this. I just want to point out a couple of my favorite features. Trust me, I spent the weekend staring at this image for hours and hours and getting more excited by the day. I've got 4 different focus boxes. Let's take a look at B. I call this one of the troublemakers. If you know the story of OSIRIS-REx, you know just a couple days after we collected the sample, we saw material spewing out into outer space, one of the many heart-pounding moments on this mission for me. It's because these large particles got trapped in between this flap, which was designed to keep the precious sample inside. And that's generally good news, right? Because those are big particles, and there's a lot of science to be done there. In panel C, we're just looking at some of the finer grain material, and I'm particularly interested in the different reflectance. Bennu has a salt and pepper kind of texture, bright grains and dark grains, and we're seeing that. In fact, as I was zooming around these images, I felt like I was miniaturized and running around on a tiny little Bennu. Panel D there is one of the really fragile-looking particles. It's got this kind of hummocky texture. It looks like the dark, large boulders that dominate the surface of the asteroid. And what gets me is the similar size or the similar shapes and textures, even as we go to these smaller sizes. Bennu seems to have this kind of fractal nature. And then finally, the last panel there, panel E, just shows 2 very different kinds of rocks sitting next to each other. One of our key hypotheses is that there's 2 major different kinds of rocks on the surface of the asteroid, darker and brighter, weaker and stronger, and we may see those already represented. And just recall, this is the material that leaked out of the tag SEM when we flipped it over. Underneath that flap, there's a whole treasure chest of extraterrestrial material, and trust me, the sample science team can't wait to get their hands on it.
Thank you, Dr. Loretta. Now let's hear from Dr. Daniel Glavin, OSIRIS-REx sample analyst.
Okay, thank you. So we've heard a lot of exciting stuff already about the water and how Bennu could possibly contribute to our oceans. I'm here to talk about carbon. Why is carbon so important? Well, carbon is essential for all life on Earth. We are all carbon-based. Carbon forms bonds with hydrogen, oxygen, nitrogen, and the sulfur to form prebiotic and biological compounds that are important, amino acids that are part of our proteins and enzymes. We even look for nucleobases, components of the genetic code in DNA and RNA. So exciting stuff, and one of the reasons we want to look for this material in these samples is to understand whether asteroids like Bennu could have not only delivered the water that led to our oceans, but actually seed the Earth with prebiotic chemicals, right? The building blocks of life. And this is the part I just find really exciting. So let's get right to it. The first carbon measurement was made at the Carnegie Institution for Science. We heard it from NASA Administrator, about 5%. The actual number is 4.7%, close to 5%. And this was a big deal. At the time this data came back, I mean, there were scientists on the team going, wow, oh my God. And when they say that, scientist says that, wow, that's a big deal. So we were excited right away. In fact, Carnegie said this for the extraterrestrial samples they've analyzed, this is the highest abundance of carbon they've ever measured in any extraterrestrial sample. And they've analyzed close to 250 meteorites. So this is a unique sample that we're dealing with. The second measurement we made, we started to look more at what is the nature of this carbon. You're looking at an image here. Oh my gosh, this was taken in the optical microscopy lab right here at Johnson Space Center. gorgeous image of a particle of Bennu. On the left, you see a small grain of Bennu in reflected light, visible light, like you'd see with your eye, but magnified. And on the right, you see the same grain, but under UV ultraviolet light. So this is like the crime scene investigation TV show where they go in with the black light and they look for the evidence that they can't see with their naked eye. We're doing the same thing here now, but with a 4.5 billion year old grain from the early solar system. And the stuff's lighting up. You see carbon there in the center, just to the right, the kind of a light bluish fluorescence. That's from a carbonate mineral, so carbon locked up in this mineral grain. But then you see these small specks of light, looks like stars, right, glowing. This is organic matter. Call these organic globules. And I know the analyst at the time who made this measurement said, you know, this thing's loaded with organics. I mean, again, just, you know, this is incredible material. Still a lot of work to do, and we're just beginning here. We're just literally scratching the surface of what's in this material. But we'll be looking for these, again, biologically essential organic molecules over the next month as these samples will go out to labs around the world to study this in more detail. And I want to make just kind of one final point. We've heard about these great initial preliminary results. I know there's more to come. But OSIRIS-REx, the team, we picked the right asteroid. And not only that, we brought back the right sample, right? This stuff is an astrobiologist's dream. You know, just can't wait to get at it, and this material will be around for generations and generations. We're going to learn so much about the origin of the solar system, the evolution, and potentially how even life started here on Earth.
Thank you, Dr. Glavin. Next up, and finally, we'll hear from Dr. Lori Glaze, Planetary Science Division Director.
Shaniqua. It's such an honor to be here today, and what an incredible honor to share the stage with these amazing scientists up here. You know, we're just, you know, within NASA, we're so proud of everything that is gone on so far with this mission. We're so excited for everything yet to come. But I want to note, you know, just beyond the folks that are here, the folks that you saw working in the lab, there's a whole team that's been spending incredible hours over the last 2 weeks to bring you the information that you saw today and to make these early discoveries. It's just an incredible team. They're working really hard, and you know, we keep telling them, don't, you know, take your time, go slow, but they're doing an amazing job. It's really incredible. But as you heard, what you're seeing here today, as exciting as this is really just the beginning. There is so much incredible work to happen. We're going to get that tag SAM opened up. We're going to get the full sample. We'll really get a full picture of what we collected and begin those amazing discoveries. But let me put OSIRIS-REx in a little bit of context about some of the other planetary work that we're doing at NASA. So within our NASA planetary program, we actually have almost 40 missions that are exploring the solar system. Some of those are being developed, some of those are in operations. But within those almost 40 missions, we actually have 7 of those missions that are focused on understanding asteroids. And you heard from Dante about how important asteroids are for understanding the early formation of our solar system, the origin of life and water on Earth, and perhaps other places in the solar system. These asteroids are really, each one of them in different parts of the solar system can give us different pieces of the puzzle about where we came from. And of those 7 missions, right now, we're really lucky because we're in the middle of what we're calling asteroid autumn. We've got several big milestones happening right now on 4 of those missions. Of course, you know we got the OSIRIS-REx sample that landed on September 24th. Right after, 20 minutes after the entry system was released from the spacecraft, we actually transitioned that spacecraft for a new mission. It's now called OSIRIS-APEX, and that's a mission to go explore the Apophis asteroid. We're actually going to rendezvous with Apophis in 2029, so they've got another long journey and another great goal for that spacecraft. And then 2 days after the OSIRIS-REx samples landed in Utah, we celebrated the 1-year anniversary of the double asteroid redirection test. And you heard Senator Nelson at the beginning mention that, what an incredible feat that was, the first time ever for humanity to change the orbit of a celestial body. And the first time we've demonstrated our ability to protect ourselves from a potentially hazardous asteroid in the future. So now we're celebrating OSIRIS-REx here today, the sample reveal. And then coming up in November, November 1st, we have another mission that's going to explore a special set of asteroids that are even much further out in the solar system. They lead and trail Jupiter in its orbit around the sun, and those are called Trojan asteroids. That mission, called Lucy, is actually on November 1st going to fly by a main belt asteroid on its way out towards the Jupiter system. And it's going to fly by a main belt asteroid called Dinkinesh, and it's going to allow them to test out all of their operations as they fly by the asteroid. And then finally, the big one that Administrator Nelson also mentioned is that we have a mission called Psyche going to visit a unique asteroid, one of only 9 out of several million asteroids that we believe are out there. There's only about 9 or so that we've discovered so far that we think are really enriched in metal, iron and nickel. And so the Psyche mission is going to go visit that asteroid, 16 Psyche, and we hope to launch it tomorrow. In fact, I'm getting on a plane this afternoon to go back to Florida to hopefully wish it off the surface of Earth tomorrow, but we've got so many opportunities for that to happen. And so that's the next big thing. Pay attention for that one. And with that, I'm going to hand it back to Shaniqua.
Thank you. Thank you, panelists. We will now move on to our Q&A segment. We'll be taking questions from media in the room and students from the Houston and San Antonio Independent School Districts. We'll take our first question from media. If you'll come to the mic one at a time, you'll be able to state your name and affiliation. And if you know where your question is going, please direct it to one of our panelists.
Hi, I'm Andrea Leinfelder of the Houston Chronicle. I have a question about the tag SAM. Did you guys expect it to be open now? And has there been any reason it's not open? Have you run into any problems or anything that just made the process slower than expected? Thank you.
So the only problem is a great problem, and that's we've found a lot more sample than we were anticipating before even getting into the tag SAM. And because we need to very meticulously and carefully collect every grain, it's taking us a little longer to get inside, but the view so far is amazing.
Our next question we'll take from students. If you come up to the mic and tell us your name, grade, and school, we'll like to hear from you.
Hello. I don't think it. Hello. Oh. Hello, I'm Allison Cordova. I'm in 6th grade from D Middle School, and my question is, do you think the samples got affected from the heat when entering our atmosphere?
I'll take that one. No, because the sample return capsule, you can see our engineering model. So this is what we did all of our practice with. That white nose there is a heat shield. And it's made of very special material that protects the sample inside. And one way to think about it is when the astronauts come back from the space station or from the moon, they have a similar kind of capsule. The astronauts land safely, just like the sample did. So that heat shield took all of the heat through the passage through the atmosphere, keeping that sample pristine and safe inside.
Thank you.
Thank you. We'll take our next media question.
Hi, Eric Berger with Ars Technica. Congratulations, those were some pretty stunning images of what we saw. I guess my question is for Dante Loretta. I know you haven't opened up the tag SAM to look at all the rocks and hopefully inside, but I'm sure you've done a mass analysis of the spacecraft versus what you've got now. And so what is the estimate of the total amount collected versus the minimum goal of 60 grams?
Great, thanks, Eric. Great to see you here. So we were able to do a mass estimate in flight, and that's not an easy thing because you're in a weightless environment, right? You're in microgravity around the asteroid. But tag SAM, the filter, was at the end of a long robotic arm, about 9 feet long. And as we moved that arm before sampling and after sampling, we were able to look at a property called momentum that was transferred between the arm and the spacecraft. There's special components called reaction wheels, which will take up that momentum. And we looked at that difference, and we estimated about 250 grams or about 8.8 ounces of material. So we're hopeful about 4 times the mission requirement is still to be revealed inside tag SAM. But of course, the proof will be when we open it up and we actually get it on a balance here in our Earth's gravity field and get that real number for you.
All right, we'll take our next student question.
Hello, I'm Raj Sinha from Houston, Texas. I am a junior at Langham Creek High School and a NASA SEAS high school intern. And this is a question for anyone. What are the broader implications of the OSIRIS-REx mission for our understanding of asteroids, the early solar system, and potentially hazardous space objects?
Well, you think about the formation of the universe and then the formation of our solar system, and there's this gas and this dust that's all swirling, and things start to be created, and then all of these things start running into each other. And out of it come stars, and then lesser celestial bodies start getting within the gravitational pull of that star, but there are still these particles that are running through space that are ramming into each other. That is going to be the clue for us examining an asteroid like this and the others that Lori Glaze mentioned, as we try to understand those questions that I posed when I was up there at the microphone. Who are we? How did we get here? Where are we in the vastness of this cosmos? And this, by the way, is fulfilling part of our destiny. And part of our destiny is that we are explorers, we are adventurers. We want to know what's over there in order to know why we're here.
All right, we'll take our next media question, please.
Hi, I'm Mike Prokosh. I'm with the NASA Social and the same Houston State University. And I was wondering, how did the rotation rate of the asteroid influence the choice of the landing zone?
Great question. So one of the criteria when we selected the target for the mission was its rotation rate, because if an asteroid is spinning too quickly, being able to match that velocity and make a safe contact with the surface would have been impossible or really, really difficult. So it was originally, when we were going through the millions of asteroids that Lori mentioned, to pick the one that you send the spacecraft to, the rotation rate was important. The surface is moving about 10 centimeters per second, so just a few inches per second, so really slow relative to what we can do with the spacecraft. And at the end, right before we sampled, we had to match that rotation. It was the final maneuver we called the match point. So we were essentially hovering over the sampling location, and the spacecraft just dropped down for that gentle contact to collect the material.
Thank you.
Thank you. All right, we'll go to our student question. Again, please state your name, grade, and what school you attend.
My name is James Johnston. I'm a senior in high school, and I go to CETA High School at Roosevelt in San Antonio. And my question is, where did the Bennu asteroid come from?
Where did Bennu come from? Maybe it's a Danny.
It's a great question. That's what we're trying to figure out. Certainly we think, originally it was part of a much bigger parent body, probably 100-kilometer, somewhere in the asteroid belt, maybe towards the outer parts of the asteroid belt, and then was broken apart, right, by an impact, and we're looking at kind of the remnants of that, a rubble pile, if you will. So some of those pieces came back together, and then it ended up, kind of in this near-Earth orbit. But we're trying to figure out really the history of that process, when those things happened, where it originated. That's part of our major science goals here, and by studying these samples, we're going to be able to answer that question in more detail than I can give you right now.
Thank you very much.
All right, next media question.
Hi, Kaylee Brower with NASA Social and Harvard Smithsonian. I was curious about the appeal of the larger rock samples, such as the one trapped under the flap on the canister, versus the smaller dust and rock samples.
Yeah, I'll take that. So we're excited about the whole size range of what we see there, because that'll tell us about the different formation mechanisms of the stones. So the big ones are really good because you get the minerals in context to each other, which mineral is next to which one. That'll give you some indication of the chemistry that happened inside the asteroid. Minerals will convert when the water hits them. You take a normal rock and you add water and you get the clays. And we might even see the original rock inside and that where the water was reacting, and that might be frozen. So it gives you that context and that big picture. The fine particles I'm particularly excited about because I think they were bigger stones when they were on Bennu in the microgravity environment. And then when they got to Earth's gravity, it just crushed and fell. And something like that would not make it to the surface of the Earth as a meteorite. And so that, to me, as I grew up studying meteorites, in college and in graduate school, so to have something from space that we've never seen in our laboratories, there's nothing more exciting. No matter what it is, the fact that it's new has got us really anxious to get that material into our instruments.
Incredibly cool. Thank you.
All right, we'll take another student question.
All right. Hello, I am Aaron Kingsland from Lavernia, Texas, a junior at Idea Carver College Preparatory School and the NASA SEAS High School intern. My question is, what ripple effects do you anticipate the OSIRIS-REx accomplishment will provide for both space exploration and our world, given the historical precedent of these achievements driving unexpected advancements in various fields?
At NASA, we're doing 100 things at once. And this is just one example. Dr. Glaze mentioned a whole bunch of others, but we haven't even talked about what is one of the primary purposes of the Johnson Space Center, which is human spaceflight. Look at the breakthroughs that are coming now, finally coming to fruition in pharmaceutical research on the International Space Station. It's just unbelievable. Now we are going back to the moon after a half century, not just to go to the moon. We're going back to the moon in order to learn, to live, to create, to invent, in order to go to Mars and then beyond with human beings. Again, it's part of our nature as adventurers, as discoverers. And by the way, this didn't just start with us. We happen to be a new world that happened to have a European discoverer experience it. But before that were the indigenous peoples, and they discovered. So somewhere deep inside our core is this yearning to learn what's out there. Now we are playing the discovery in such a large, large playfield called the universe. And we find from James Webb, we find that after a NASA scientist who got the Nobel Prize, by the way, discovered that the universe is 13.8 billion years, we are beginning to see that light as a result of the telescope. 1 million miles from Earth, we're beginning to see that light in the formation of the first galaxy. So there's still so much more to discover, and you're going to be part of it. And by the way, you're one of our high school interns. You keep at it.
Thank you.
Thank you.
All right, we'll take another one from media.
Hi, Robert Perlman.